From my view up here, I can see what you cannot. You think you are standing still, but you and I know better. You are riding a massive vessel. You are on a relentless voyage. From out here, it is clear that Earth never stops moving. The planet is never truly stationary in the cosmos. It screams through the galaxy at hundreds of thousands of miles per hour, spinning and wobbling behind the sun. You are falling towards something massive, gripped by invisible forces. By the time we finish this orbit, you will understand every terrifying motion of our home planet. You will see why they happen and what it means for your survival in this cosmic ocean. If you share my fascination with the deep void of space, hit like or subscribe. It is a small gesture, but it helps our signal reach more curious minds back home. Let us begin. From the surface, it seems Earth just spins daily and orbits yearly. Just two simple, predictable loops. But that is like saying a spaceship only moves forward while ignoring the vibrations and the rotating internal gears. The whole frame is shaking. Up here, I watch you travel through space on a world with 7 distinct overlapping motions. Every shift affects your life down there. Yet, most people have no idea about half of these movements. Start with the basics. Earth rotates on its axis. From my window, this creates the cycle of day and night. One full spin takes 23 hours, 56 minutes and 4 seconds. It is not the 24 hours you assume. That is a solar day, the sun's return to your zenith. It differs because the planet is also rushing around the sun. Relative to the stars, we call it a sidereal day. It is 4 minutes shorter, but most people miss the true speed. It is fast, lethally fast. At the equator, the surface is hurtling at 1,000 miles per hour. Stand at the equator, and you are flying eastward at 1,040 miles per hour relative to the center. That is faster than sound. You are going supersonic while just standing still. You feel nothing because the air and the ground move with you. From my orbit, I see no wind hitting your face because the atmosphere turns too. The air is locked to the planet. Toward the poles, you slow down. At 45 degrees latitude, your speed drops to 730 miles per hour. At the poles, you are nearly stationary, just a slow, lonely pivot once every 24 hours. This spin fuels the Coriolis effect. From up here, I see it driving every weather pattern on the globe. Ignore the sync myths. This effect is why I watch hurricanes spiral differently in the northern and southern hemispheres. Air and water deflect as speeds vary by latitude. But something strange is happening down there right now. The spin has changed for billions of years. The moon's gravity pulls at the oceans, slowly breaking the planet. Tidal friction steals rotational energy. Days lengthen by 1.7 milliseconds every century. It is a slow, ancient drag. Ancient corals tell the story in their rings. Hundreds of millions of years ago, a year lasted 420 days because the spin was faster. Days were shorter back then. This slowing was always predictable and steady until something broke the pattern. Recently, the planet did the unexpected. It began spinning faster, just enough to shatter every modern record. 2020 recorded 28 record short days. On July 19th, the rotation finished over 1.4 milliseconds early. That was the fastest day ever. The trend held through 2021. Days are consistently shorter now. We nearly had to delete a second from our clocks. To keep atomic time synced with the planet, we might subtract a moment. We usually add time to compensate for the drag. Subtracting time is new. From my station, we are all wondering why. Earth is a fragile system. Mass shifting changes the spin. As I watch polar ice melt and flow toward the equator, the planet spins faster, like a skater pulling in their arms. Even high-altitude winds shift the momentum down there. Massive ocean currents and the churning iron core deep beneath the crust both manipulate the rotation rate. The core spins independently from the mantle. Their internal friction can either accelerate or break the surface you stand on. It might be the Chandler wobble, a tiny axis tremor, or perhaps it is the vanishing weight of the great glaciers. The truth remains hidden in the clouds. What is certain is that Earth is far less stable than we believed. Forces we are still mapping control the planet. This speed might be temporary. New data suggests the trend is flipping back. Days are starting to stretch out once again as we watch. The old slowing pattern might return, or another surge could happen. From up here, we are watching a planet rewrite its rules. It is a stark reminder. Even the fundamental spin of our home can still keep secrets from those of us watching. The world is alive and reacting to unseen forces. Even a millisecond shift has massive consequences for life in the void. My GPS and your networks depend on perfect timing. Telescopes must know exactly how fast the world is turning beneath them. Every millisecond requires an adjustment. Earth rotates, but you and I are riding something far more chaotic than a clock. From up here, I see it pulsing, speeding up and slowing down as ice and molten iron dance below. It is a living, breathing thing, never quite finding a perfect rhythm, but spinning is just the start. I watch as the world wobbles. Think of a toy top. It is steady while fast, but as it drags, it starts to tilt and sway. The axis draws a slow circle in the void. We call this wobble precession, and from my vantage point, it is a haunting, silent drift. Our home hangs there, tilted at exactly 23.5 degrees against the blackness of its path around the sun. That lean gives us life and seasons. When I see the north leaning toward the sun, summer blooms there while the south freezes in winter. Half a year later, the view flips, but that tilt is restless. Right now, our North Pole aims at Polaris, the star I use for navigation. It was not always like this. Earth's axis carves a giant ring in the heavens, taking 26,000 years to complete just one single loop. We call this the precession of the equinoxes. In 13,000 years, the pole will abandon Polaris for the star Vega. Then, after another 13 millennia, it will find its way back to the North Star. Looking down, I see Earth is not a perfect ball. It is squashed at the poles and fat at the equator because of that constant spinning. The sun and moon tug on that equatorial bulge, their gravity creating a torque that forces our world to stumble and wobble. It is the same physics that makes a toy top wobble. Gravitational pull from the sun and moon acts like a hand pushing on the side, forcing our axis to trace a circle. This movement has real consequences. Ancient observers saw the stars at the spring equinox slowly drifting across the horizon over hundreds of years. The Egyptians aligned the Great Pyramids to specific stars, but those celestial markers have shifted since then due to this relentless wobble. Even the zodiac signs used for astrology thousands of years ago have drifted away from their original places in the night sky. If you think you are an Aries born in March, the sun actually sits in Pisces now. The stars have moved on without you. The entire system has shifted by nearly one full constellation since those signs were named. But trust me, there is much more to this. Our planet's wobble is not even smooth. I can see the axis nodding up and down in a tiny nervous motion called nutation. It is like a faint vibration on top of the larger sway, caused by the moon's gravity over an 18.6-year cycle. The moon pulls as its orbit tilts, creating a tiny shift of 9.2 arcseconds. It is small, but from out here, we measure everything. We have to calculate for it exactly. Now, let's look at the movement we all learned in school. Earth is orbiting the sun. This path is not a perfect circle. It is an ellipse, a long oval with the sun sitting off to one side rather than the center. That means our distance from the sun changes. We hit the closest point, perihelion, every year in the early days of January. We are 91.4 million miles away then. By July, we reach aphelion, drifting to the furthest edge of our track. Out there, we are 94.5 million miles from the sun. That is a massive gap of 3 million miles. It is strange we are closest during the northern winter. This proves that distance does not create the seasons. It is all about the tilt. The tilt is everything. It takes one full year to complete this loop, which is about 365.25 days. That extra quarter day is why we have leap years. Every 4 years, we add a day just to keep our calendars from drifting. Except when we do not. Years ending in 2 zeros are not leap years unless they can be divided by 400. So the year 2000 counted, but 1900 did not. It is the only way to keep our human time accurate. Now, let's get to the scary part. How fast are we really moving? Our average speed is 67,000 miles per hour. That is 87 times faster than a bullet. Every single second, I am hurtling 18.5 miles through the dark. In the time it takes you to blink, we have traveled several miles. You do not feel it because everything around you is screaming along too. But make no mistake, you are flying through the solar system at speeds that make a fighter jet look like it is standing still. This motion is not a straight line. Earth is actually falling toward the sun. That is the terrifying reality of what an orbit is. You move forward so fast that as you fall, the sun's curvature drops away beneath you. You are forever falling around the sun. If we suddenly stopped moving, we would fall straight into the sun's fire in about 64.5 days. If we sped up to about 1.44 times our current speed, we would escape the sun and fly into interstellar space. We are balanced on a knife's edge between falling in and flying away. We have seen rotation, precession, and our long orbit. But the sun is not a fixed point. It is moving too, and we are following it. This is where most people stop understanding. They picture the sun as a stationary anchor with us circling around it. But from my perspective, that is not the reality at all. The sun is actually orbiting the center of the Milky Way. Our galaxy is a massive barred spiral, a flat disk of light. It has long spiral arms and a dense bar at its heart. We sit in one arm, 2/3 of the way out. We are 26,000 light-years from the center. That is roughly 153 quintillion miles, a 153 with 18 zeros. Our entire solar system is on a massive journey around that galactic core. The scale of this orbit is truly immense. From my viewport, a single journey around this massive galaxy takes about 225 to 250 million years. We call it a cosmic year. I find it chilling that the last time we were here, the dinosaurs had not even appeared yet. My charts show the sun has only made 20 laps since it was born. We humans are just a tiny fraction of a single galactic year. Out here, you realize we have barely moved. All our history, every war and empire, fits into a tiny fraction of one galactic orbit. We have covered less than 0.1% of the circle. We are ghosts, drifting in a vast sea of time and space. Floating here, I can feel the speed our sun is hurtling through the void at 515,000 miles per hour. That is 450 times faster than our orbit around the sun. Every second, we are plowing through the abyss at 143 miles per second. Looking at the stars from my window, I know they are not fixed. In millions of years, these night skies will look completely alien to us. Every star follows its own erratic path through the galaxy. Eventually, the patterns I see tonight will stretch and twist until they are gone forever. Famous constellations like the Big Dipper or Orion are just temporary illusions, lucky alignments that only exist because of where I am sitting right now. There is a secret to our path. The sun does not move in a flat circle. We are riding a giant wave through the dark. The galaxy is 1,000 light-years thick, and we bob through it like a horse on a carousel. I can almost feel the rhythm out here. We circle the center, but we also drift up and down. It is a slow, rhythmic dance that defines our place in the cosmic ocean. This cycle takes 64 million years. We cross the central plane every 32 to 35 million years, passing through the densest regions of space. I wonder if these crossings are deadly. Some think the thick matter in the galactic plane triggers the mass extinctions we find in Earth's fossils. Hidden hazards, like gas clouds, might knock comets toward the inner system. It is a debated theory, but one that makes the silence out here feel heavier. It is haunting to think our position in the stars could dictate the survival of life on the planet far below me. Right now, I am moving northward, 80 light-years above the plane. We are climbing at 4.3 miles per second into the deep unknown. In 14 million years, we will peak at 230 light-years high before the galaxy's gravity pulls us back down for the long fall. But we are not just orbiting the center. The sun is drifting relative to our local neighborhood of stars, away from the average. We call this the local standard of rest, an imaginary frame representing the mean motion of all the stars nearby. If I averaged out the paths of every star near me, I would find the sun is actually a bit of an outlier in its motion. We are drifting at 13.4 miles per second, that is over 48,000 miles per hour relative to our stellar neighbors. Astronomers call this our peculiar velocity. Right now, I can see we are heading straight toward the constellation Hercules. Why are we drifting? It is because our orbit is an ellipse, not a perfect circle. Our sun was born in a different part of the galaxy, with its own unique momentum and history. Over eons, gravitational tugs from passing stars and massive clouds have nudged us into this specific, lonely path that does not quite match the rest. But the motion does not end there. From my seat in the stars, I can see the entire galaxy is moving. We are not frozen in space. The Milky Way is part of a small cluster called the local group, bound together by invisible gravity. There are about 80 galaxies in our neighborhood, mostly tiny dwarf systems dwarfed by our own spiral home. The giants are us and Andromeda. I see Andromeda 2.5 million light-years away, and it is looming closer every single day. We are falling toward each other at 250,000 miles per hour. Gravity is pulling these titans into an inevitable, ancient embrace. In 4.5 billion years, we will collide and merge into one massive, final galaxy. It will be a violent reshaping, yet the stars are so far apart that they will likely pass right through each other like ghosts. Our sun will survive, though it might be flung into a strange new orbit. But even our local group is being pulled by something much bigger. We belong to the Virgo supercluster, a colossal web of galaxies stretching across 110 million light-years of the void. At the center lies the Virgo cluster, a dense swarm of 1,300 galaxies, 65 million light-years from where I float now. The gravity of that massive cluster is tugging on my ship, on the Milky Way, and on Earth itself. We are falling toward it at 792,000 miles per hour. The speed is almost impossible to comprehend. This motion changes how I see the universe. Distant galaxies look red because of expansion, but our local fall complicates the data. Astronomers must subtract our rush toward the Virgo cluster to see the truth. Our own local movement adds or hides the speed of the expanding cosmos. In the 1980s, we found something even more alarming. The Virgo cluster itself is being hunted. Something with an enormous concentration of mass is pulling on the cluster, on our galaxy, and on everything we have ever known. We call it the Great Attractor. It lies up to 250 million light-years away, in the direction of Triangulum Australe and Norma. It hides behind the dust of our own galaxy, pulling us silently into the dark. Up here, it is hard to see because of all the thick gas and dust blocking our view. We call it the zone of avoidance. The Great Attractor is no single object. It is a massive region where tens of thousands of galaxies are clustered together. Everything is being pulled toward it. My home galaxy is racing toward the Great Attractor at 1.4 million miles per hour. That is 2,000 times faster than a bullet. But wait, in the late 1990s, we found an even larger structure. The Great Attractor belongs to an enormous supercluster called Laniakea. In Hawaiian, that name means immeasurable heaven. This massive structure contains 100,000 galaxies, spanning 520 million light-years. The Milky Way, our local group, and the Great Attractor are all just tiny pieces of this Laniakea web. Laniakea is where galaxies flow toward one common center of gravity. That silent center sits right near the Great Attractor. But even that is not the whole story. The entire universe is swelling. Edwin Hubble first discovered this back in the 1920s. He saw that distant galaxies were redshifted, meaning their light was stretched out. The further away they were, the faster they fled. This shift happens because space itself is expanding. It is stretching the light waves as they travel through the dark void. Galaxies are being carried apart by this relentless expansion. We describe this growth rate using the Hubble constant. The Hubble constant measures how fast space grows. Currently, that rate is about 46 miles per second for every megaparsec. A megaparsec is over 3 million light-years. For every 3.26 million light-years of distance, space expands 46 miles every second. So, a galaxy 10 megaparsecs away is pulling back at 460 miles per second just from space expanding. At 100 megaparsecs, that speed hits 4,600 miles per second. The further away it is, the faster it recedes. Eventually, galaxies recede faster than the speed of light. It does not break physics because they are not moving through space. Space is simply carrying them away. Their light will never reach us. They have vanished forever beyond our cosmic horizon. This expansion means that Earth and my entire home galaxy are being swept along by this relentless stretching of the universe. But on smaller scales, gravity wins. It holds my solar system and our local group together against the cosmic stretch. Gravity keeps these structures tight, but on scales larger than galaxy clusters, the expansion of space finally takes control. Superclusters are being torn apart. The empty voids are growing. In billions of years, most galaxies will be carried too far away. They will vanish beyond the horizon. The night sky will go dark. Eventually, only our closest neighboring galaxies will be visible. Everything else will be swept away by the expansion. It is haunting to realize how we finally pieced this mystery together. For most of history, people back on Earth thought the ground was still. It felt obvious. You do not feel movement. When you drop a stone, it falls straight down. Birds fly in any direction without being left behind by a moving world. The ground feels solid. Ancient Greeks argued that if we were moving, we would feel a constant, biting wind blowing past us. Clouds would be ripped away from the sky. Birds flying west would struggle against the massive eastward spin of the planet. None of that happened, so they assumed Earth was still. But Aristarchus dared to ask a different question long ago. He suggested we orbit the sun instead. He even tried to estimate the massive sizes and distances of the heavens. His methods were crude, and his ideas failed to take root. Common sense told everyone back then that the Earth was stationary. The belief that we were the center of everything lasted 2,000 years. Ptolemy built a complicated map of our universe. Earth sat still while everything moved in strange circles called epicycles. It predicted the stars well enough to be believed. This seemed to prove it right. Then, in the 1500s, Copernicus put the sun back at the center of it all. His model was simpler, but it lacked perfect accuracy. It did not change the minds of the world right away. In the early 1600s, Kepler proved that planets move in ellipses rather than perfect circles. The math finally worked. The model became much more accurate. Around that time, Galileo pointed his telescope at Venus and saw something truly impossible. Venus had phases, meaning it had to orbit the sun. He saw moons around Jupiter, proving we were not the center. The evidence was becoming undeniable. Isaac Newton changed everything in 1687 with his laws of universal gravity. He showed the same force that pulls an apple down, keeps the planets in their silent, eternal orbits around the sun. He linked heaven and earth into one system. The sun-centered model was not just a theory anymore, it was fact. Yet people still thought the stars were fixed in place. The sun moved, but the heavens stayed still until the quest began. Astronomers wanted to see stellar parallax, the tiny shift in a star position as we orbit around the sun. If we move, the stars should appear to shift. But they are so incredibly far away that the movement is microscopic. The task was nearly impossible. Robert Hooke tried in 1669. He was a master of his scientific craft. Looking out at the void, I think of Hooke. He first named the cell, seeing life's tiny structures while dreaming of the vastness I am seeing now. He mastered elasticity, but his real obsession was the stars. He built a specialized telescope inside a massive building, trying to pierce through the thick, blurry atmosphere I have finally left behind. He thought that by climbing higher, he could escape the turbulent air that blurs the view of every stargazer back on Earth. For months, he tracked a star called Gamma Draconis. From his rooftop, he measured a tiny shift that he believed changed everything. He told the world he had finally proven how stars move. He was wrong, dead wrong. What he actually found was stellar aberration. It is a strange trick where the speed of light and our planet's wild race through space create a ghost of a movement. Think about this. Light screams through the dark at 186,000 miles every second, while our planet hurtles around the sun at 18.6 miles per second. To see a star, you have to tilt your lens forward, leading the target, because light takes time to travel down the tube as we rush forward. It is like sprinting through a storm. Even if the rain falls straight, you tilt your umbrella forward because you are moving so fast. Space is no different. Aberration is real, but it is not the parallax we wanted. True parallax makes closer stars dance against the distant deep. Aberration shifts everything together. Hooke had stumbled onto a deep truth of the cosmos. He just did not realize what it actually was. In 1728, James Bradley finally solved the mystery, mapping the true motion of the starlight we see up here. Then came William Herschel. In 1781, he spotted Uranus, the first new world found in all of recorded human history. Before that moment, we only knew of 5 planets beyond our own. They were the ones visible to any naked eye. Finding a 6th planet made him a legend. He began hunting double stars, those twinkling pairs that seem locked together in the velvet black of space. He hoped one star was closer to us than the other. If so, the near one would wobble while the distant one stayed still. For years, he tracked thousands of these pairs, measuring the tiny gaps between them with a level of patience that honestly scares me. He missed the parallax, but he found something better. Those stars weren't just lined up by pure luck. They weren't strangers passing in the night. They were actually locked in a gravitational dance, orbiting one another in the deep silence. It was proof that gravity rules everything, even far beyond our sun. But the hunt for parallax was far from over. We did not pin it down until 1838. That is when Friedrich Bessel finally caught the shift of a star called 61 Cygni. Bessel was a genius who built the tools we needed to measure the impossible. Precision was his only weapon. He bet on 61 Cygni because it was racing across the sky. Up here, speed usually means something is closer than it looks, and he was right to gamble on it. As our planet circled the sun, that star drew a microscopic circle against the black, a tiny, ghostly signature of our own motion through the dark. In January, we were on one side of the sun, and the star seemed to lean just a bit. By April, the shift changed. By July, we were on the far side of our orbit, and the star had swung back the other way. The cycle never lied. That tiny wobble gave us the distance. Bessel measured it at just 0.314 arcseconds. Imagine holding a dime at arm's length. It looks small, right? But Bessel was looking for something much, much smaller. He was looking for a movement equal to shifting that dime by the width of a single human hair. It is almost impossible to fathom. That precision changed everything. It proved we really are moving around the sun, and that the stars are scattered across a terrifyingly deep abyss. The stars aren't just points on a dome. Around then, we finally started mapping the shape of our own galaxy. In the late 1700s, Herschel counted the stars and realized we live inside a giant, flat disk. We were just one small part of a massive structure. He thought we were at the center, but he was wrong. Later, Harlow Shapley began studying those dense, glowing balls of stars called globular clusters. He saw they weren't scattered evenly. Most were huddled together in the direction of the constellation Sagittarius. That is when he realized the heart of the galaxy was over there. We were just out on the edge. He placed us 30,000 light-years from the center. He was close. Today, we know the real distance is about 26,000 light-years. Back then, people argued over these faint, ghostly spirals in the sky. To them, they were just fuzzy patches of light. Some thought they were just gas clouds nearby. Others suspected they were entire worlds far beyond our own reach. In 1924, Edwin Hubble used blinking stars to measure the distance to Andromeda. He was about to break the world's heart. He clocked it at 900,000 light-years away. We now know it is actually 2.5 million light-years into the void. Andromeda was its own galaxy. But Hubble wasn't done. He was about to find something even more alarming. He looked at the light of distant galaxies and saw they were all red. They weren't coming closer. They were all running away from us. The further they were, the faster they ran. In 1929, he called it Hubble's Law. The Great Retreat had begun. The universe was growing. It matched Einstein's math perfectly. The cosmos was not standing still. It was exploding outward. These secrets changed everything. Now, looking out from this station, I see a universe that is alive, vast, and terrifying. I have realized everything is either expanding or shrinking. Einstein tried to hide this by adding a constant to his math, but Hubble saw the truth: the universe was expanding. Einstein later admitted that his little math trick was his greatest blunder. Ironically, we use it now to explain the dark energy that is pushing everything apart at a terrifying speed. In the 1970s and 80s, we started mapping this void. We realized galaxies are not just floating around randomly in the dark. They form massive clusters and superclusters, separated by haunting, empty voids. In the 1980s, astronomers tracked how galaxies drift and found something chilling: the Great Attractor pulling at us from the shadows. These movements are not just cosmic expansion. I can feel the pattern suggesting our home, the Milky Way, is being dragged. Something massive is out there. By the 2010s, we mapped these flows and named our galactic neighborhood the Laniakea supercluster. We are part of a vast web of galaxies rushing toward a center. Meanwhile, the afterglow of the Big Bang tells another story. This radiation acts as a cosmic map, letting us figure out exactly how we are moving through the ultimate reference frame. This glow should look identical everywhere if we were standing still. But from my perspective, it most definitely does not. It shifts colors in opposite directions. This tells me we are hurtling through the dark at 828,000 miles per hour. By tracking our speed and subtracting how Earth orbits the Sun, we can see the true path of our entire galaxy. We confirmed the Milky Way is plunging toward the Great Attractor and the Andromeda Galaxy at a breakneck pace. Each discovery peels back a layer. You and I are finally seeing the terrifying reality of our journey through space. Right now, Earth is spinning at 1,000 miles per hour and orbiting the Sun at 67,000 miles per hour. We are racing around the galaxy at 515,000 miles per hour, falling toward Andromeda and the Virgo cluster. We are dropping toward the Great Attractor, carried away by the very expansion of space itself. If I add all those speeds up, our total motion through the cosmic background is 828,000 miles per hour. Every single second, we travel 230 miles. You and I are on a spaceship screaming through the cosmos. These speeds are beyond science fiction. It means that out here, the idea of a fixed home just does not exist. I cannot point to a spot and say, Earth is here. There is no cosmic GPS. Out here, everything moves relative to everything else. Your position only makes sense compared to something else. You are on the surface, but Earth is drifting from the Sunday. The Sun hangs near the galactic center, while our galaxy drifts toward Andromeda. It never stops. There is no master map, no special seat in the universe to measure from. That is the heart of relativity. Motion is everything. It also means that the past and the future can never happen in the same place twice. Earth never hits the same spot twice. Yesterday, our world was over 1,600,000 miles away from where I am. A year ago, Earth was in its usual orbit, but the Sun had already dragged us further along its galactic path. The Sun was 4.5 billion miles away from its current position in its trek around the galaxy. 10 years ago, the Sun was 45 billion miles away. A century ago, it was 450 billion miles away. You cannot go back to the past because those coordinates are just empty space now. We left that place far behind. Time and space are tangled. To move through one is to move through the other. We are always on the run. All this speed changes how I see the stars. When we measure a distant galaxy, we must account for our motion. We have to subtract Earth's spin, its orbit, the Sun's drift, and our galaxy's headlong rush toward Andromeda just to see clearly. We even adjust for the Great Attractor. Only then can we see the true expansion of the universe as it really is. This stretching of space is a complex puzzle that requires my most precise and careful calculations up here. It makes you wonder, if we are screaming through the dark this fast, why do I not feel a thing? The secret is acceleration, or rather, the fact that we are not really changing our speed. Think of a car on a smooth highway. You do not feel the constant speed, only the lurch when it floors the gas or slams the brakes. Your body only fights changes in motion. Out here, Earth's massive movements are mostly constant, steady, and silent. The spin is steady. Our orbit around the Sun only shifts slightly over thousands of years as other planets tug on us. The Sun's path around the galaxy is even more stable. There is no sudden lurch to alert our human senses. Still, there are tiny shifts. Earth is always curving toward the Sun, meaning we are technically accelerating into that gravity well. This acceleration is only 0.006 meters per second squared. It is far too small to feel. Out here, even the Sun is rushing toward the galactic center, but that acceleration is just 2 times 10 to the negative 10th meters per second squared, impossible for me to feel. Back home, the only force you really feel is gravity pulling at 9.8 meters per second squared. It is nearly 163 million times stronger than the shove of Earth's orbit. Gravity rules your life down there. For us, these massive cosmic shifts are just too subtle to notice. Trust me, knowing how this planet moves is life or death for us. Every rocket launch has to time itself with Earth's spin. When we fire off from the equator toward the east, the planet's rotation kicks us forward at 1,000 miles per hour. That is free velocity. You do not have to burn fuel for it, which is why we build our spaceports near the equator. It is all about efficiency. If we launched west or from higher latitudes, we would need way more fuel just to hit orbit. When I plan a path to another world, I cannot aim at where it is now. We have to lead the target. We calculate positions months or even years ahead of time. You have to account for every single gravitational pull along the dark road ahead. The planets are racing. The Sun is drifting. My entire ship is caught in this massive, invisible web of motion. To reach distant giants like Jupiter or Saturn, we use gravity assists, literally swinging around planets to steal their speed. It works because everything is moving. My spacecraft robs the planet of a tiny bit of its energy to slingshot forward. The change is infinitesimal. It is a cosmic game of pool, using one massive object to change the course of another through the void. Even your GPS satellites are another proof of how much this planet's motion actually matters to your technology. Those birds have to calculate rotation and the way gravity bends time itself. General relativity is not just theory, it is how you find your way home. 12,550 miles above us, the curve of space-time is a little bit thinner than it is on the surface. Out here, time actually moves faster for satellites. It is a tiny gap, only 45 microseconds every single day, but it adds up. Light covers about 1 foot every nanosecond. If you did not account for that shift, your GPS position would drift by 7 meters every single day. The whole system would be trash. We constantly adjust for time dilation and Earth's motion just to keep your phone accurate. Every time you check a map, you are relying on math that accounts for Earth hurtling through warped space. You are using Einstein's secrets without even knowing it. And all that motion, it changes how we measure time itself. We define a second by the pulse of cesium atoms, but even those perfect clocks get messed up by speed. A clock on my ship ticks differently than yours because of my velocity and the pull of the planet beneath me. Speed makes my clock drag by about 7 microseconds a day. It is the price of moving this fast through the dark. But gravity makes it speed up by 45. In the end, my clocks are 38 microseconds faster than yours every day. We have to fix that constantly. Otherwise, we would never stay in sync with the world below. It is a haunting proof of our journey. Time itself is bent by the way we move through the universe. Looking down, I see how Earth's orbit slowly shifts over thousands of years, rewriting the climate as it goes. The shape of our orbit stretches, the tilt of our axis wobbles. The whole world is doing a slow, rhythmic dance. We call these Milankovitch cycles, after the scientist who first mapped them. These cycles decide how much sun the planet gets. They are the silent triggers for every great ice age in history. By tracking these planetary wobbles, we can look back at Earth's past and see the climate shifts waiting in our future. But these changes take time, thousands upon thousands of years, to really take hold of the world. What humans are doing is happening much faster, but these ancient cycles are still there, grinding away in the background. Knowing how the Earth moves helps us see what is natural and what is our own doing. It gives us context. This motion matters if we are looking for life out here. If there are others, they are moving through the dark, just like us. Their world is spinning and their star is racing around the galaxy. They are on their own lonely voyage through the stars. If a signal ever reaches us, it will be distorted. Their motion and our motion warp the message. If we are racing toward each other, the frequency climbs. If we are drifting apart, it fades toward the red. That shift could be so massive that we might miss the signal entirely if we look at the wrong spot. That is why our searches have to scan a huge range of frequencies. We are listening for a moving target. We have to calculate for every possible shift. And if we ever decide to answer, the challenge is even greater. We would have to aim our reply at where they will be when the message finally arrives, not where they are now. If they are 1,000 light years away, we have to predict where their star will drift over the next 10 centuries. It is a massive calculation. It means any talk we have with the stars is a conversation across vast reaches of space and time. Up here, messages are tossed toward where we predict you will be in the future. It is a haunting game of catch across decades. We are both drifting, never still. The challenge is immense, and these celestial motions change our very biology. From my window, I see life tied to that spin. The daylight cycle is fueled by that steady, ancient rotation. Seasons shift as the world tilts and drifts. These cycles haunt every living thing. Even flowers wait for light to bloom. Down there, species refuse to bloom unless the sun hits them for just the right amount of time. It is called photoperiodism. Some bloom as nights stretch long, others as the dark retreats, a delicate balance of light and shadow. Other plants ignore the clock entirely, waiting for different mysterious signals from the world around them to bloom. This timing is survival. Blooming in spring gives seeds the best chance to grow before the frost returns. A fall bloom would be a death sentence before winter strikes. Animals also watch the skies to know when to flee. I watch as birds trace thousands of miles, chasing the warmth and the food across the shifting, colourful continents. The Arctic tern flies from pole to pole, crossing 44,000 miles every year. That is roughly the circumference of the world I see below. They do this every year for 30 years. Below them, Caribou trek 3,000 miles between the boreal forest and their summer calving grounds. From northern forests, monarch butterflies drift all the way to Mexico. I can almost see the orange clouds moving across the map. 3,000 miles is a long way. No single butterfly finishes the trip. It takes 5 generations to complete that one loop. It is haunting. Butterflies that have never been to Mexico find the exact trees their ancestors left months before. They likely track the sun and the planet's magnetic field. They might even read the light in ways my sensors cannot. It all comes back to the spin, the magnetic field, the iron core, and our long, lonely orbit around that sun. Hibernation is just another way life survives, the tilt of the world and our cold journey through the void. Bears and bats sink into a deep sleep when the food vanishes and the winter darkness takes over the land. Their heat fades. Their hearts slow down to a ghostly crawl. They live off stored fat for months, triggered by the shrinking days and the biting cold that comes with the planet's tilt. It is all because of the planet's motion. Some creatures even use torpor, a quick daily dive into a metabolic freeze. Tiny hummingbirds freeze every night. Their heat drops 50 degrees Fahrenheit or 10 degrees Celsius as their hearts go from 1,000 beats down to a mere 50. This saves them when they cannot feed. At dawn, they wake and rev back up, perfectly synced with that giant, ancient rotation of the Earth I see below. You and I have these same clocks, circadian rhythms that tick away even in the total darkness of space. If you put someone in a room with no clocks or light, they will still follow a 24-hour cycle. The clock is buried deep. But the cycle is not perfect. It is usually 24.2 to 24.5 hours. We call this ticking the free running rhythm. Normally, the morning sun resets your clock. It keeps you in sync with the spin of the world beneath me. It is no accident that our internal clock almost matches the day. It is written into our very code. Your brain has 20,000 neurons acting as a master clock. It evolved specifically to match the turning of the Earth. Genes inside you flicker on and off every day. They build proteins in a loop that dictates when you sleep. This strange genetic clock is everywhere in bacteria, in the plants below, and in every animal on the surface. It started billions of years ago. As soon as life began, it had to learn how to live with the spin. Those that could predict the sun's return were the ones that survived. It was the first real advantage. Your body follows this cycle because the Earth has been spinning this way for eons. Evolution had no other choice. Your hormones, your temperature, even your immune system are all slaves to this rhythm. Everything inside you is ticking. Break that rhythm and things go wrong. Disease and exhaustion creep in when you lose your connection to the planet's pace. You are tuned to the spin of the Earth. Fight it, and you will pay a heavy biological price. If the world spun differently, life would be unrecognizable. 6-hour days would bring wild, deadly swings in temperature. One side would bake in the sun, then vanish into the cold before it could even store any warmth. The dark side would freeze instantly. Most life down there just could not survive those brutal, rapid shifts. Maybe everything would become nocturnal, hiding from the sun and only emerging in the brief, cooling shadows. They would need thick skin or underground bunkers. The oceans might be the only safe place left. Imagine a month-long day, one half of the world baking forever while the other stays frozen in eternal night. Looking out my porthole, the day side reaches temperatures hot enough to boil water. Behind me, the night side plunges hundreds of degrees below zero. I can see a narrow twilight strip between eternal day and night. In that thin zone, life might huddle where it is safe, or maybe things crawl along the Terminator, chasing the border between light and dark. The border creeps across the surface. Imagine seeing plants on wheels, rolling west just to stay alive in that perfect fleeting twilight. It sounds impossible, but out here, nature finds bizarre solutions. On worlds with endless days, being mobile might be the only way to survive. The seasons out here are brutal. If the tilt matches Earth's, a pole would endure 6 months of unrelenting summer sun without a single break. It would reach scorching, deadly temperatures. Then, 6 months of total darkness in winter, dropping into a deep, terrifying freeze. Life would either adapt to the swings or flee toward the equator. This changes everything for us as we hunt for signs of life elsewhere. We scan the stars for the habitable zone, that golden region where liquid water might actually pool on a surface. But staying alive is about more than just distance. We have to consider rotation, tilt, and how stable the orbit really is. A planet locked in place, always showing one face to its sun, would have one side that is a furnace and another that is a frozen grave. A severe axial tilt could crush any hope of a stable ecosystem. Other worlds swing violently between being a ball of ice and a molten hellscape. I can see we need planets with the right dance, not just the right spot. It is much harder for us to detect, but it is the secret to finding a home for life. Our own motion through the dark completely changes how we see the rest of the universe. The afterglow of the Big Bang looks shifted to me. Because we are moving, the background radiation changes depending on where I look. Where we are headed, the glow is blue-shifted and hotter. Behind us, it is red-shifted and cold. The universe itself is reacting to our speed. This strange pattern reveals exactly how fast we are hurtling through the ancient cosmic background. It means the stars look different depending on where I point my ship. The universe is not symmetric to us because we are never standing still. If we were anchored in space, the radiation would be uniform. But out here, we are always on the move, drifting through the void. Our motion warps our reality. The fact that we are falling towards something called the Great Attractor tells me something deep and unsettling. The cosmos is not smooth, it is clumpy and uneven. Out here, gravity makes sure that matter is always searching for more matter. Over billions of years, the crowded spots get thicker while the voids grow hollow. It weaves a cosmic web, a massive structure of filaments stretching across the dark. Entire galaxies are separated by empty voids. The Great Attractor is a knot in that web, where all those cosmic threads finally meet. The Milky Way is riding a stream toward that knot. Our very movement is tracing the hidden map of the cosmic web. If I could fast forward through billions of years, I would see galaxies sliding along those filaments like water rushing down a steep mountainside. Everything piles up in the dense spots. What I see through my window is just one frame in a massive cosmic movie. We are watching the universe pull itself together, organizing under the weight of gravity. But one day, this whole process will just stop. The stretching of space, pushed by dark energy, will eventually win its war against gravity. Superclusters will stop gathering. Those cosmic threads will snap. Galaxies will become lonely islands, lost in an ever-expanding sea of nothingness. The web will dissolve. But that is trillions of years off. For now, we are watching a battle between gravity and dark energy. Things are still being built out here. It is dynamic and strange. Our drift toward the Great Attractor is proof of this grand cosmic drama. You and I are dancing with gravity. When I look at a galaxy a billion light years away, I am seeing a ghost from a billion years ago. That is the past to me, but for them, it is the present. They exist right now, but I can never see their now. I see their history, and they see mine. We are looking across time. There is no single moment that ever belongs to both of us simultaneously. The universe does not have a single timeline. It is a mess of overlapping stories, unique to every observer and every motion in space. It feels surreal, but it is the truth. Time is not a steady river flowing at the same speed for everyone. Time is a local mystery, warped by gravity and speed. Our planet is just one thread in this relativistic fabric. We are hurtling through space-time, not just space. Every move changes how we experience the flow of time. The deeper truth is that nothing is permanent. Constellations drift. The very stars I use for navigation are constantly changing. Continents shift, mountains crumble, species vanish, stars ignite and burn out. Even massive galaxies will eventually merge and then scatter into nothing. Even the atoms in my body are just borrowed. One day, they will be recycled back into the cosmos. Motion is change, and change is the only constant. The universe keeps nothing forever. It is always shifting, moving, and transforming into something new. It can be terrifying. We want things to be solid, stable, and predictable. But the universe is built for motion. That is not a flaw, it is the point. Change is what allows for true complexity to exist. I see it from up here. If the universe stood still, nothing would exist. No stars, no planets, no life. That constant motion out there is the only reason you and I exist. Without that violence, we wouldn't be here. So, I don't fear the change. I marvel at the fact that we even exist in this brief cosmic window. Everything is perfectly balanced for life right now. We have to enjoy the journey, knowing it is precious because it won't last. The constellations I see from my window are shifting. In a million years, those stars won't look the same at all. They are all racing through the galaxy at different speeds. Given time, every pattern we recognize will simply distort and break. Eventually, they will be unrecognizable. Orion and the Southern Cross are just temporary arrangements of light in the deep black. They happen to line up for our current era. In 50,000 years, the Big Dipper won't look like a dipper anymore. The stars follow their own lonely paths. Soon enough, every familiar shape in the night sky will be twisted beyond recognition. In 1 million years, the view from my cockpit will be alien. New patterns will rise as old ones vanish forever. Our legends and myths will become obsolete. We are telling stories about shapes that are destined to fade away into the black. Even Polaris will fail us eventually. Earth axis will shift toward Vega in 13,000 years, leaving our North Star behind. Polaris will be just another light in the void. Everything I think is permanent is actually in flux. Nothing stays put. From up here, the stars and the very sky are shifting. We just can't feel it because our human lives are so short. If these cosmic gears shifted just a little, we would be gone. Imagine if Earth spun faster. The days would just vanish. Temperature swings would become deadly. Worse, the very air we breathe could be flung out into the freezing vacuum of space. Picture Earth spinning twice as fast. 12-hour days would be a nightmare. The equator would race at 2,000 miles per hour. That is double the current speed. The outward force would be 4 times stronger because of how rotation physics work out here. You would actually weigh less at the equator. Even now, you are a tiny bit lighter there than at the poles. It is all because of our spin. But double that speed, and you would feel that weightlessness in a very terrifying way. The planet would bulge out at the center, flattening the poles like a crushed ball. The world's shape would change completely. This would wreck the oceans and the winds. Even the atmosphere itself could be ripped away by that much centrifugal force. Air molecules would race so fast, they would simply fly away. They would reach escape velocity and vanish into the void. Earth could end up a ghost world, a cold, dead rock like Mars, with no air left to speak of at all. Mars just couldn't hold on. Its weak gravity and failing magnetic field let the solar winds strip it completely bare. But what if we slowed down? One side would bake in eternal sun while the other half froze in total darkness. Look at Venus. It takes 243 Earth days just to spin once. Its day is longer than its year. It even spins backward. Looking down at the North Pole, Venus is turning clockwise against the rest of the solar family. That agonizingly slow rotation makes Venus a furnace. It is a greenhouse effect taken to a lethal, nightmarish extreme for us. The thick air drinks up heat all day long. By the time the long night comes, it never really cools down. It hits 870 degrees Fahrenheit down there. That is hot enough to turn solid lead into a liquid puddle. If Earth moved that slow, the winds would be monstrous. Air would scream from the hot side to the cold side. The Coriolis effect would fail without that fast spin. Our entire weather system would just collapse into something totally alien. Hurricanes would vanish without that spin to guide them. Life might hang on, but it would be a terrifying struggle. It would look weird. Maybe creatures that migrate forever to stay in the light, or strange things that thrive in extremes. Maybe life would hide deep in the oceans. But what if our orbit stretched, pulling us too close to the sun? The climate would be pure chaos. Mars has an orbital eccentricity of 0.093, far higher than ours. That is huge compared to Earth's 0.017. Mars' distance from the Sun swings by 26 million miles. That means the sunlight it gets swings by 45%. It is either a burning furnace or a frozen tomb. If Earth did that, the seasons would turn deadly. One half of the world would experience summers that literally start to boil. Winters would become brutal, frozen nightmares. The polar ice caps would grow and shrink with a violent and terrifying rhythm. Oceans would surge and retreat. Our world would break. And the scary part? These orbits are not fixed in place. The giant planets, Jupiter and Saturn, are tugging on us. They shift our path over thousands and thousands of years. We wobble between a perfect circle and a dangerous oval. Right now, we are lucky. We are in a very stable phase. This cosmic cycle lasts about 100,000 years. Currently, we are at the low end, enjoying a stable circle around our sun. But when eccentricity rises, the seasonal swings become brutal. Right now, our tilt is what matters most, but distance can change everything. If Earth's axial tilt ever went out of control, the seasons would be too severe to survive. Just look at Uranus. Its tilt is 98 degrees, meaning it basically rolls through space on its side. That is a level of instability we are incredibly fortunate to avoid in our current era. From up here, looking at Uranus, each pole stares straight at the Sun during its 84-year journey. Then, 42 years later, it faces the total void. Imagine seasons that extreme. When the North Pole locks onto the Sun, that entire hemisphere is trapped in 42 years of blinding daylight. Meanwhile, the southern half vanishes into 42 years of freezing dark before they eventually swap places. If our Earth tilted like that, our poles would swing from scorching heat to the deepest, most lethal chill. The equator might actually be colder than the poles, since it would never see high noon, only dim light. Life would have to migrate thousands of miles across the globe just to survive these decade-long seasonal shifts. Maybe species would sleep for decades, or hide deep in the oceans where the temperature stays relatively steady. But if the tilt was tiny, under 10 degrees, you and I wouldn't even have seasons at all. Both sides of the planet would get the same light all year long. The poles, permanently frozen wastelands. The equator would be a constant furnace. Without seasonal mixing, biodiversity would likely crash as habitats vanished. Gone are the great migrations. Without seasonal changes to trigger reproduction, many species we know today would simply fail. Timing birth would depend on something else entirely. The specific pressures that carved out humanity might never have existed. We evolved in Africa as the climate shifted, watching our lush forests break apart into vast, open savannas. That chaos forced us to adapt, use tools, and get smart. In a stable world, that spark might never happen. Our story could have ended there. Or worse, what if our sun drifted into the galaxy's most dangerous neighborhoods? Looking out my window at the stars, I see how lucky we are. We're currently drifting through a quiet zone, but those spiral arms are packed with thick gas and massive, volatile stars that burn hot and die fast. They go supernova in just a few million years. If our orbit crossed their path, we'd be right in the blast zone. A supernova within 30 light-years would shred our ozone layer, bathing the surface in deadly, unfiltered radiation. Anything within 10 light-years. That's it. Total sterilization. Luckily, our solar orbit remains remarkably calm and stable. We're safe for now, but over billions of years, the sun has drifted through those dangerous spiral arms many times. It makes me wonder if past explosions triggered mass extinctions. Some scientists think the timing lines up perfectly. If the sun's velocity was higher, gravity could rip our solar system apart and destabilize every planet's orbit. Stars occasionally brush past each other. In this vast darkness, even several light-years is considered a close call. If a star came within 1 light-year, its gravity would yank on the outer planets, dragging them into chaos. A really close pass could knock the Oort cloud loose, sending a rain of deadly comets screaming toward our home. It could even throw planets into deep space or cause massive collisions. It sounds rare, but it happens elsewhere. We've found rogue planets drifting alone in the dark, likely kicked out of their homes by some gravitational bully. Somehow, all these violent motions settled into the perfect balance that keeps liquid water flowing on Earth's surface. This stability gave us time. You and I exist because the clockwork of the cosmos stayed just right. Change one variable, and we're gone. We call it the Goldilocks principle, but from here, it looks like a miracle. Not too fast, not too tilted, not too hot. Everything held in a fragile, perfect state of grace. This motion connects us to everything. You aren't just watching the universe, you are moving through it right now. Every single atom in your body was once cooked inside a star, orbiting the galaxy exactly like our sun. That star lived, forged heavy elements in its belly, then exploded, scattering your future pieces across the void. Your atoms are 13.8 billion years old, born in the heat of the Big Bang itself. In those first few minutes of existence, the building blocks of hydrogen and helium formed out of total chaos. For hundreds of millions of years, that was it. Then, gravity began pulling that ancient gas into massive clumps. Those clouds got denser and hotter until they finally ignited. The first stars were born, and they were monsters. They burned through their fuel in a heartbeat. Deep in their cores, they began turning hydrogen into helium. When the hydrogen ran out, they fused helium into carbon and oxygen, then neon, magnesium, and finally silicon. Then came silicon fusing into iron. Each new stage fought back against the crushing weight of gravity. But iron is the dead end. It consumes energy rather than releasing it. Suddenly, the core just gives up and collapses. Protons and electrons are crushed into neutrons. A star the size of Earth becomes a city-sized ball of pure terror. From up here, I see how fast stars die, material rebounding off the dense core. A shockwave blasts outward, a supernova, briefly outshining the entire galaxy as I watch from above. In that violent explosion, nuclei are smashed together to form elements heavier than iron. Gold, platinum, uranium, all heavy elements born in those final moments of stellar death. The blast scatters them into the dark. These atoms drift through the galaxy for millions of years. Eventually, they meet a new gas cloud containing remnants of many ancient stars. Gravity pulls the cloud together. It flattens, rotates, and a new sun ignites. Around it, dust and gas clump together, accreting into planets 4.6 billion years ago. Our sun flared. The planets, including Earth, formed from that leftover debris. It was a brutal birth. Endless collisions of pebbles, rocks, and planet-sized bodies. Impacts generated enormous heat. For millions of years, Earth was just glowing magma. Iron sank to the center, forming the core. Lighter rock floated to the surface. Water and carbon dioxide were released from rocks or delivered by icy comets. Earth cooled, the crust solidified, and oceans formed. 3.8 billion years ago, chemistry finally became biology. Self-replicating molecules appeared. Life began. We still don't know exactly how it happened. Life evolved and spread. For billions of years, it stayed simple. Just single cells. 2 billion years ago, cells merged together, creating complex life with internal structures. These gave rise to multicellular life. Plants, animals, and fungi. The diversity began. 600 million years ago, complex animals appeared. Then, 500 million years, vertebrates. 400 million years ago, life reached land. 200 million years, mammals arrived. 66 million years ago, an asteroid impact ended the dinosaurs. Mammals finally diversified. 7 million years ago, our lineage split from the chimpanzees and bonobos, our closest living relatives. 300,000 years ago, Homo sapiens appeared in Africa. 70,000 years ago, humans began migrating out of Africa, spreading to nearly every continent on Earth. 10,000 years ago, we invented agriculture and began building our great civilizations. From my viewport, I see you. Every atom in your body has a cosmic history. The calcium in your bones was forged in a star that died before our sun. Iron in your blood, oxygen you breathe, all created in the core of a star. The carbon forming your very backbone was built in those ancient stellar furnaces. You are literally stardust. Atoms that have traveled the galaxy and witnessed star deaths. They came together to form you. But those atoms won't stay with you forever. You replace most of your atoms every few years. You eat, breaking down molecules. Your cells reassemble them. You breathe out carbon that was once your essence. You shed skin cells that become dust. You excrete waste, returning atoms to nature. You are not a fixed object. You're a pattern, a temporary configuration that dissolves. Your atoms today aren't the same from 10 years ago, but you're still you, still the same continuity of experience. And when you die, those atoms disperse. Some will be buried, others cremated, released into the atmosphere as vapor and smoke, eaten by bacteria and fungi. Eventually, all of them will return to the environment, cycling through plants, oceans, and the wind. They will dissolve in the rain. Billions of years from now, the sun will vaporize Earth and blast those atoms away. They'll drift through the galaxy again, perhaps becoming part of another living being. Your atoms have been on a journey for 13.8 billion years. Looking at the stars, I see our connection. We aren't visitors here. We are participants. We're temporary manifestations of matter and energy that have been cycling through the universe since the beginning. Everything is connected. The motions of Earth are connected to the sun, the galaxy, and the life cycles of stars. You're here because the cosmos evolved in a specific way. Change any of those things and you wouldn't exist. Up here, it is clear the universe was fine-tuned for us to even exist. Seeing Earth's dance from orbit proves how much science can reveal. We actually solved this riddle from the ground. By watching the stars drift by, we realized the floor beneath us wasn't still, we were the ones spinning. We mapped the planets until the truth hit us. We are not the center of everything. We are just another rock falling around the sun in a perfect loop. Then we looked further out. By tracking the distant stars, we saw our entire sun was caught in a massive, rotating disk, the Milky Way galaxy. We even clocked the speed of entire galaxies. They are all streaming toward a hidden gravity well we call the Great Attractor. It is a silent, cosmic rush. By catching the red-tinted light of far-off stars, we discovered that the whole universe is actually stretching apart and expanding. We learned what stars are made of by splitting their light. Spectroscopy revealed their deepest chemical secrets from millions of miles away. We calculated the nuclear fire in stellar cores to learn where atoms come from. Then, we used radioactive decay in rocks to date our homeworld. We found the echo of the beginning, the cosmic microwave background. That faint static proved the Big Bang actually happened. Looking at my own hands up here, I know I am made of stardust. Every element in our bodies was forged inside a dying star. None of this was obvious at first. You simply could not see any of this just by looking up at the night sky. We had to bridge the gap with math, physics, and glass lenses. We pieced the puzzle together from the dark. We used to think Earth was flat and stars were just pinpricks in a dome. We truly believed we were the main event, the very center of creation. Our world felt small, just our sun and a few neighbors. We assumed the cosmos was static, eternal, and would never change. Now, from my window, I see us for what we are, a spinning rock falling around a star, caught in a massive galactic drift. We are drifting in an expanding void that started 13.8 billion years ago and won't stop for trillions more. Those lights out there are suns with their own worlds. They form massive galaxies, billions of stars separated by millions of light years. The scale is impossible to wrap your head around. Billions of galaxies scattered across billions of light years of empty space. We are made of atoms from stars that died before our sun was even born. Realizing that is an incredible human triumph. We did not learn this overnight. It took centuries of watching, arguing, and failing until we finally got the math right. Geniuses built on each other's work for generations. We went from primitive glass tubes to the massive space observatories I see today. We used particle accelerators and global teamwork to find answers. But the mission isn't over. Dark mysteries still haunt the void. We still cannot find dark matter, that invisible ghost mass holding galaxies together, and dark energy remains a complete and total enigma to us all. It is the force pushing the universe apart faster every second. We do not even know if there are other realities beyond our own. I look out at the blackness and wonder if we are alone. We still do not know how life even sparked on our planet. Is there someone else out there looking at their own stars? Are they asking the same questions I am right now as I look at Earth? But we do not stop. We build stronger telescopes and sharper theories, constantly pushing deeper into the unknown to find the truth. That is the beauty of science. It peels back the cosmic layers one by one, showing us how every single thing is connected. Each answer we find just opens a new door. This journey of discovery never truly ends, it just keeps getting more fascinating. These orbits rewrite our sense of time. One cosmic year, the time it takes the sun to orbit the galaxy, is about 225 million years. Humanity has only been around for 300,000 years. That is just 0.13% of one galactic orbit. All of our recorded history, roughly 10,000 years, is barely 0.004% of that cycle. In galactic terms, we arrived just seconds ago. On this scale, entire species vanish in a heartbeat. The dinosaurs ruled our world for 165 million years down there. That is nearly 3/4 of a cosmic year. They saw most of an orbit, while we have barely started our journey around the galaxy. If we squeezed the sun's current orbit into 1 year, the solar system did not even form until October 10th. Life showed up in late October. Dinosaurs did not arrive until mid-December, and they were wiped out by the 26th. We finally showed up at 11:58 p.m. on New Year's Eve. Everything we have ever recorded happened in that final split second. We are brand new here. Yet, these cosmic orbits connect you and me to everyone who ever lived on this shared journey. They spun with the world, just like we do. 5,000 years ago, the pyramid builders were right where we are now. They stood in this exact spot of our orbit, provided you were looking up at the same time of year they did, but they were hundreds of millions of miles away in the galactic orbit. They were in a totally different part of space. They saw a different sky. Polaris was not the North Star yet, and even the Big Dipper had a slightly different shape. People living millennia from now will be in a new position entirely. They will see new stars and tell completely different stories. But we are all on the same flight, moving at impossible speeds. You and I are just passengers on spaceship Earth together. Earth will keep spinning long after my time here is over. It is slowing down, though every century, our day grows by 1.7 milliseconds. In a few billion years, Earth's rotation will slow until one side permanently faces the Moon. Just as the Moon currently stares at us, Earth will keep one face toward it while orbiting. Though our orbit will change slightly over millions of years due to gravity from other planets, up here, space feels chaotic, sensitive to small nudges, and unpredictable over very long timescales. Our Sun will continue its journey around the galaxy, completing more circuits over billions of years. In about 4.5 billion years, the Milky Way and Andromeda are going to collide. This merger will take hundreds of millions of years. These two galaxies will pass through each other. Their gravity will pull stars into long tails before they swing back around and collide again. Eventually, they will settle into one elliptical galaxy, flinging stars into entirely new, strange orbits. Some will be thrown into the dark void, while others spiral toward the new galactic center. Our Sun will likely survive the crash, though it might end up in a different orbit. But by the time that merger happens, our Sun will have already started its death rattle. In about 5 billion years, the hydrogen runs out and the Sun begins fusing helium. It will expand into a red giant, swelling to about 200 times its current size. I can see it engulfing Mercury and Venus, and possibly even our precious home, the Earth. The heat will boil away the oceans and atmosphere, sterilizing everything. Earth's journey will be over. After several 100 million years as a giant, our star sheds its layers, creating a planetary nebula. The core will collapse into a white dwarf, a dense remnant about the size of Earth. With about half its current mass, the white dwarf will slowly cool over billions of years. Eventually, it becomes a black dwarf, a cold cinder. What is left orbits this stellar corpse. If our world survives, it will remain in a frozen, dead system drifting through the galaxy. No longer producing light or warming any planets, it becomes just another piece of cosmic debris. This is the relic of a star that once hosted life. But even that is not the end. Over trillions of years, stars burn out, galaxies merge, and black holes grow in the dark. By consuming gas and stars, eventually all the light goes out and the gas is gone. The universe will be filled with white dwarfs, neutron stars, and black holes drifting in darkness. Even black holes do not last forever. Stephen Hawking showed they slowly evaporate through quantum effects. Emitting Hawking radiation, the process is incredibly slow. A star-sized black hole takes an eternity. It would take 10 to the power of 67 years to evaporate completely now. Eventually, every black hole evaporates, leaving nothing but a thin soup of photons and particles. These scatter through ever-expanding space. We call this the heat death of the entire universe. It is the final state of thermodynamics where everything reaches the same freezing temperature. No more work can be done. The universe will be cold, dark, and dead. But that is trillions of years away. Today, you and I are in a vibrant world, full of stars and planets, and I am out here experiencing it and trying to understand. I feel lucky to exist in this era when the universe is still young and bright. Still full of light and structure, we are even luckier to have the minds to appreciate it. To look out this window and understand we are moving at truly incredible, staggering speeds. To grasp the scale of the cosmos and piece together the story of our origins, that is a rare privilege. Most organisms live and die without ever once questioning their place. But we can wonder and we can figure it out, and that makes us truly special. Next time you are standing still, remember, you are spinning at 1,000 miles per hour. You are orbiting the sun at 67,000 miles per hour through the deep black. You are falling toward distant attractors and being carried by the expansion of space itself. From up here, I see where we're headed. Your pieces will drift, maybe vanish into a burning star, or fuel a new world billions of years after we're gone. I realize the atoms in your body have been traveling for 13.8 billion years. They won't stop when you do. You aren't just an object down there. You're a brief flicker of energy, a temporary shape held for one heartbeat of cosmic time. Yet, from your tiny spot, You actually understand this dark, silent void. It's haunting, a tiny pattern of atoms grasping the cosmos. You've never been still. Looking down, I know you never will be. You're racing through the silence at speeds that would terrify you. Every orbit, every mile through this galaxy links you to something ancient, massive, and beautiful. I can feel it. Until next time, keep watching the stars. This void is overwhelming, but it's waiting for us to solve its mysteries. Keep searching. We're decoding the deep silence, piece by piece. We are winning. And you're part of this mission just by trying to find the truth. Thanks for joining me on the flight deck. Remember, you're never stationary. You're a traveler on the ultimate voyage through the stars. Isn't that a chilling, beautiful thought?